this is Brianna, and to get started, let's address a few logistics. Everyone's mic is muted throughout our time together. If you have any questions, please ask them within the questions pane. We will have a representative answering questions as well as a Q&A at the end. Jerry Long will be our presenter today. He is an application engineer and has been involved in product lines such as verification, simulation, and timing analysis. So with that being said, over to you, Jerry.
All right, thank you, Brianna. Hello, everybody. What I'm going to talk about today is basically some tools you may not know you have, and then kind of go into an extension of those types of tools available to you through the new Aurora product that Cadence has recently released. So first of all, I'll start with what you may not know that you have, basically in the OrCAD PCB Designer Professional line and the Allegro PCB Designer. There's essentially some new features kind of waterfalled in, as they say, from, I believe they put them in originally around QIR7 in the 17.2 release. So these have been around a little while, probably coming up on a year or so now. In terms of availability. So they're basically, if you're familiar with the Sigrity Electrical Rules Check, the ERC capabilities, they're basically that technology, that capability kind of waterfalled into the PCB editor product. So I wanted to show you what you had if you have these OrCAD Design Professionals, and then show you basically what you can move up to, what you can expand on to that level of technology. And this is all just maintained all within the PCB editor environment. You're never leaving this environment to do these capabilities. So I'll start with OrCAD PCB Designer Pro. That's the license I currently have. And what I'm going to do is basically show you these particular tool sets and how to access them. So the first thing you need to do is once you launch the tool, you need to go to the Analyze pull down and launch the Workflow Manager. And this will be available here. It'll come up depending on where you last launched it. This is a floating window, so you can move it around anywhere you want. I got mine just kind of added up here with the other tabs for fine visibility and options. But basically, the analysis workflow is where you launch the new tool sets, the new capability. Now, with the OrCAD Designer Pro, you just have a couple of tools at your disposal, and they're basically impedance workflow and coupling workflow. What these tools do will essentially analyze the nets of your choice, and you can have it look at the entire board if you like. But what it's going to do is it's going to look at these nets of interest, and it's going to track from starting point to destination point the impedance that that particular net is seeing or basically presents. And so all of the individual segments, all the bends, the turns, the neck downs, the escapes out of pin arrays, all of those particular areas of those traces will be analyzed for impedance, and it will show you what how those impedance changes along that particular trace route. Same thing for coupling. It's going to do the exact same thing, look at all those signals of interest and show you how much coupling you have between adjacent nets and nets that are in the immediate vicinity above and below. So let's start with impedance. I've selected the impedance workflow. What you'll essentially do next is essentially tell the tool what analysis mode you want. You can have it look at either all net-based or directed group. We'll start off with net-based. And then the next step is to go out and tell the tool which specific nets you want to analyze. And in this tool flow, once you select that, it's going to present the list of nets for the board. I'm just going to grab about 15 or 16 address lines, and then about 16 data lines, and then I'll go grab some strobes here. So I'll grab the strobe 0 and 1 for the first two byte lanes, both negative and positive for the differential pairs. Add those to my analysis, select OK. Now the tool knows that I'm going to go and analyze these particular nets. It knows what nets to go focus on, so it gives me a green check mark to say that's set up correctly. Next is analysis options. With impedance, there's not a whole lot of options. There's just one particular option if you have any kind of coplanar traces on the board. This particular board has no coplanar traces, so I'm not going to enable that option, but that's the option for impedance. And then the next thing is just kick off the analysis. So what it's going to essentially do is go through and analyze each of those selected nets, and then it's going to present in tabular form the results, and it's going to present in what they call a vision form as well. So it's already done with that, so now we can go look at what we have. So we did a net-based analysis. So that's my view mode. I want to stay in net-based analysis. And we can look at either single-ended or differential pairs. I'm going to look at single-ended here. The first thing we'll do is look at the impedance table. So if I select that, it's going to give me the list of nets that it analyzed. And it's going to give me kind of a summary table up top, which is the net and kind of some totality of the information on the net. And then as I select individual nets, you'll see in the bottom portion of this table, it's going to give you kind of a breakdown of that particular net, all the segments that are involved in it. So if I want to, if I'm concerned about impedance, for instance, I want to come over, I want to sort on the maximum impedance that it sees, so I can see, some problematic traces here. And in this case, there's a couple of, 120 ohm resistance that it sees, 120 ohm impedance. If I take a look at that and kind of analyze what it's telling me, it's basically saying, yeah, these may jump way up, but it's a very small, insignificant part of the trace, so it may not matter in this case. But as we further go down, maybe this one, DQ15, maybe that one might make some significant problems. So because it's 1% of the trace, it's not the the 0.01% like those other ones are. So if I select that, it's going to give me some details down here, and what I'm really interested in is I want to know where that 77 ohms came from. So I can sort on this lower one as well. So this is all the segments that make up DQ15. And now I see the two segments that are reporting 77 ohms. So what I can do here is look at the associated length. And this one looks to be 28 mils right here. So let's go see where that is. That's a 78, or let's look at the 77 at 26 mils. So if I double click on that, it's going to jump immediately to that location on the layout where it saw that impedance jump up. So if I kind of back out a little bit, there's my trace, DQ15, and so this is the area where it's saying that I'm getting 77 ohms. And so, one thing you may want to do is come in here and see why that may be. So in my case, I think this is most likely going to be due to going, yeah, right there. So it's basically routed in a void between planes, between power planes and ground planes. So if I turn that on, the ground looks pretty good, but the powertrain has some voids in it. So the power plane is probably what this is reporting against for that jump up in impedance. So it's kind of that's the kind of indications you're going to get out of the table. You can sort on specific characteristics of what you're seeing, hone in on exactly where that is on the board, and then determine whether or not that's a significant amount of change to make a difference in your design. So that's the table approach. The other approach is the vision. So if I close the table down and turn on impedance vision, I'll kind of back out a little again here, kind of zoom into my initial area, turn off my planes so we can kind of see what's going on. So this is going to give me kind of an overall what they call a layover of the board, and it's going to essentially give me through this graph here, through this legend, color-coded legends, it's going to give me a breakdown on the impedance that it reported. So here I see most everything's in the 50 to 70 to 80 ohm range. Well, in this case, 50 to 60 ohm, most of the traces that you're looking at. But it does see some that jump out here, that jump up into the red, the 126. And this is those high impedance areas that we saw on the table. We can also see where they occur here in this fashion. This just kind of gives you an overall look. Once again, we can turn on the ground planes and whatnot to see, why that is. And you'll see exactly, if I turn on a ground plane here, you'll see exactly where that is in the adjacent layers to these traces. You'll see those are jumping up in high impedance because there's basically a keep out area in the ground plane there for pads and pins for these connectors. This is a DDR2 board, or DDR3 board, excuse me. Has a controller here in the middle and then two SDIMM sockets right here. So that's kind of what you're looking at for impedance. It'll come in and let you show visions where you can see overall for the layover of the board and where exactly some problematic areas may be through color coding, or you can hone in on specific results out of the tables. So that's the impedance flow. Let me go back and turn the ground plane off, kind of get back to a normal view. And we'll go ahead and go back to turn Impedance Vision off. The next thing I'll show is coupling. So if we want to go to a coupling workflow, again, you're going to have to go through and set up, basically tell the tool what what nets of interest that you want to be analyzed. So in coupling mode, you have, again, a net-based or a directed group, but we could do this with a directed group here. So I'll select a directed group mode. And this is going to come up with a directed group panel that you can select essentially what you want. Now what you're looking at is a menu here, a panel where you can go and create those directed groups. So you typically go in and create directed groups based on byte lanes, or maybe it's just communications between the memory device and the controller overall, things like that. But this is a filter area, so you can turn off things like connectors and things like two-pin devices, resistors, inductors, and capacitors. You can also hone it down to things of 100 pins or more, and that kind of filters down the selection of what's available here for a start component and an end component in your directed group. So here I'll start with U1, which is my controller. I'll end with J1 and J2, which are my essentially my SDIMM sockets for my memory devices. Now you can see all the componentry that it's selected with all those connections. I'm going to just create that directed group. So now I have a valid directed group created. You'll see that directed group up here. And you can scroll through to see its contents. There's basically two directed groups that are created for each of the J1, J2 sockets for my SDIMMs. So once I got those created, I'll click OK. And this time, rather than just to save some time, I'm not going to actually run the simulation. I'll just load in the simulation. I ran it before, so I'll just load in the analysis. But the other thing before you start that analysis is you may want to take a look at some analysis options for coupling. And this is where you can direct the tool to, what level of coupling do you want it to report. And in this case, it's going to report back anything that's 2% or higher with a rise time analysis of 50 picoseconds. You can also set a geographic window if you wanted to, if you want its visibility to extend beyond each trace a certain amount of, a certain distance, a certain amount of mils. You can set that here as well to either create a larger or smaller geographic window. Once I select OK, then that's obviously the things you've set up for the options, and then you click on Start Analysis again. And in this case, I'm just going to load up the results. Here's my directed groups here, my results there that I've already created, and it comes up in a Visions window by default. So this is the visions of what I just ran. So you can kind of see overall some of the directed groups of this particular run between these between this DDR3 and its controller. You can see that the legend here color-coded to coefficients. So this runs from either a minimum of 0 up to a 21% coupling coefficient. So you can kind of see where most everything here is around the 10 range. So you can kind of narrow down and see where all of this coupling is occurring. You see most of it's occurring because of parallel trace runs. Another way to look at this is through the coupling table. So again, it will present a table. And in this case, it's going to show basically just either in a worst case mode or a victim mode. Right now I've set up to worst case mode. But you can run down the list of coupling analysis that it sees. You can sort on coefficients. So if we start looking at the highest coefficients and then begin to look at why they're being reported, obviously we're getting a very high coupling coefficient, mainly because of the strobes we selected. So those are supposed to be coupled tightly. So that would make sense that you would see that. But in other areas, like for instance here, I have an address line and a DQ37 line as the aggressor, giving me an 18% coupling coefficient. So in this case, you might want to investigate why that is. You can double click or single click there to get some details down here. Again, you can come in and then do a sort on the coupling coefficient. Here's the highest portion of that. So A10 and DQ37. So if I double click on that, it's going to jump to it again, and there's basically why you're seeing that. You see the DQ, the address 10 and the DQ37 just below it, so they're just running above each other, parallel in a layer above and below each other. So that's kind of why you're getting that coupling coefficient there. Let's see, there's also a victim mode you can use as well. So that I won't necessarily go into that, just interest of time. I want to show some more capabilities. If you take this concept of working within the PCB editor for this types of analysis, you can take it to the next level with the addition of the Aurora tool set. So let me go ahead and set that up. So to start off Aurora, all you do basically is enable the license. So the first thing you would do is come over and change the editor. And in this case, I'm going to select my Aurora license. I've already got that saved on, so I don't need to save that data. Let me kind of center where I am a little bit. So now I have my Aurora license enabled. If I go and look at my workflow manager, now not only do I have impedance and coupling, but I have some other modes of workflows, like crosstalk, reflection, return path, and IR drop. Let's look at IR drop first, because that's the most unique one added in that's you know, in typical tool flows, you typically don't see something like this available. So let's take a look at IR drop workflow. So what this is going to report based on the power planes that you select. It's going to report essentially where the voltage is dropping. Once the voltage comes onto the board and propagates all the way across to power devices, it's going to go through and show you, based on the amount of copper that's on the board and the areas that it has to progress through, it's going to show you how much that voltage is dropping by the time it gets to its destination. So that's the intent of the IR drop workflow. It's based on a power tree setup, which defines your VRMs and your sinks. And this is a setup that's basically I've already set up here. If you open that up, it's basically going to load up. Now, what this does is it tells the tool where your power comes onto the board, how much that power is, the value, the voltage values, the VRMs are, the voltage regulator monitor module. And it also contains sinks, all the ICs that are connected up to that plane, how much current you expect them to draw. So it's going to load that in and then begin its analysis. The analysis options here, you can set up some thresholds, some temperature rise thresholds, some trace current density. So you have a bit of control over what you can set up for a little bit of the option capability. And then when you start analysis, I'm not going to kick it off here. It does run pretty fast, but I've got some other things to show, so I'm just going to load up the results. So once you run it, it's going to kick it off and basically give you the essential results in either an IR drop version or vision or an IR drop table, either one. So if you look at the table, it's basically going to give you the listing of supplies that I had it analyzed, and this was the VDD and ground supplies, and then a VCC 1.2 volts and a 2.5 volt. So it's looking at that, it's looking at the nominal voltage setting, the actual voltage that it saw, the IR drop, the most IR drop that it saw. Tells you kind of a pass-fail status if you have some constraints in there where there's, you know, minimums or maximums that it must meet. And then it'll basically start to give you breakdowns of the actual voltage on that particular plane, you know, the voltage selected. So in this case, I'm looking at everything. In this sink voltage is what it's looking at right now, but it did run on just about all three of those planes. The more interesting way to look at this, though, is through the visions. So if I'm in IR drop mode, so I'm looking at the delta, the drop in voltage, but I want to look at power planes. Right now, it's just looking at the top of the board. I'm mainly interested in areas of power in the board. So this is the area of interest in this case, where I have power coming on over here, and it's propagating over to power certain segments of my DDR controller here. So you can kind of see once it starts getting into this pin field, it starts to drop some voltage, and it's mainly just because the amount of copper available for the propagation is starting to reduce. So you kind of see based on the colored grid, the colored legend here, it drops from a very minimal, like 10 millivolts or 0.01 millivolts, I believe is what that is, up to 17 millivolts at the worst case, which is like over in the far end of the pin grid. So 17 millivolts is not that much, so you know, maybe that's fine for this particular device's sensitivity, its power sensitivity. Another thing you may want to look at besides IR drop, you can also look at the actual voltage. This is pretty much uninteresting because you're looking really at a 2.5 volt plane, so 17 millivolt drop on a 2.5 volt plane, you don't really see it show up. But the more interesting thing here is current density. This will show you where your current is flowing through the copper and the paths that it's taking through the copper area. So this will show you essentially in units of amps per millimeter squared where your current is collecting. So in this case, there's quite a bit of current density right in here, so you may want to take a look at that, maybe beef up some extra copper in here, maybe make it a little thicker, or maybe there's some alternative paths that you can you know, expand this plane out to try to reduce that current density. You can also take a look at vector mode in here for, you can turn on show vectors. This will show you direction, you know, current direction and intensity as it goes through as well. So you can kind of see all the currents propagating through this particular area. Quite a bit of current right in here directed through this narrow area. So you may want to take a look at why that particular thing's happening. So that's IR drop. So that's, again, keep in mind, we haven't left the PCB environment at all. We just kind of switched over and loaded in a basic file that gave a listing of VRMs and sinks and where they're located and their values. And then the tool did the analysis for us and presented any possible problematic areas. What we can also do is switch over to Crosstalk workflow. Crosstalk is added with Aurora, as well as reflection and return path. So quickly, crosstalk and reflection are similar in the sense of how they present the information. Obviously, they mean two different things in analysis, but let's take a look at crosstalk. So if we look at crosstalk workflow, we're going to go through enable that mode. And in this case, what the tool needs is some kind of default model setup, some kind of modeling setup. You can set up these devices with IBIS models that you're going to use, or you can use the default topology models that Cadence provides. Some of their model drivers and receivers, you can use those. That's what I'm doing here, as opposed to coming in and using the managed libraries or the AMM model manager. If you're familiar with SigXP flows, the AMM model, the analysis model manager, is essentially just a library manager that allows you to store models like IBIS models or sync models or VRM models or just about any kind of simulatable model. It allows you to store it in there, and then you can assign it to various devices on the board. So that's kind of what this is about. You can go to the model manager, load it up, load the particular library, and assign models if you wish. You can also manage those libraries, which libraries are active, which libraries are going to be used into the model manager, and then finally do the actual model assignment. So I didn't go through the AMM in this flow. I just used some default models. So if you select this box here, it'll use a default model setup that basically will go and assign some Cadence default models that are included in the PCB editor tool for drivers and receivers. So this will just give you some responses, some details. So once you set up your drivers, the next thing is to tell it which nets you're going to run. Again, I'm not going to go through any more setup. You've kind of seen me do this before. You just select the nets of interest and add them to the side. Instead, I'm just going to skip this step because it's exactly the same of what you've seen before. I'm just going to load up some existing analysis that I've already done with Crosstalk. So if I load that up, this is again going to present in a Visions or a Crosstalk table. If you look at the Crosstalk table, it's going to basically give you kind of a Crosstalk victim with each of its neighbors. You know, kind of a mode of analysis you want to look at there. But as you go through, it'll show you, for instance, if you want to look and sort on this, you can also sort, you know, which is the most aggressive victim or the most, I guess, violated victim, if you will. And you can also take a look at the actual signals themselves. So if you click on that highlighted area, that hyperlinked area, it's going to bring up a plot of the actual signal that it sent down that aggressor's path to see what the victim held quiet. It's going to show you what is induced onto that victim trace. So that's what the signal looks like. Most violated victims here in this search order for Crosstalk. So you can kind of take a look at that. By the same token, you can also look at reflection. So crosstalk is where you're holding your victims quiet and then sending signals down the aggressors. Reflection is just what's going to happen when you send a signal down that particular trace. It's going to see a certain change in impedance flow and report back either some oscillations or some overshoot, undershoot kind of results. So that's what we're looking at in reflection workflow mode. So in this case, this is a good impedance checker or impedance verifier. You can set up a modeling. Again, I'm using just default models, but the modeling setup is very similar to crosstalk. Again, you can select your nets. This is identical to the flows you've seen so far. You select the nets for analysis. Here, I'm just going to load in some results for crosstalk, or I'm sorry, for reflection. And then again, you can look at it in a vision flow where you're looking at a ringback margin is what it's keying on for the results here. Basically, the kind of ringback that it sees on each particular net after sending a pulse down the circuit. Most everything looks pretty good in this case. Everything's roughly in a very low voltage range, anywhere from 0 to 0.8 volts. So pretty well below the my switching threshold of interest here. But you can also look at it in tables. So if I want to go here and look at the table again, you can sort on the ringback margin. And again, you can select any one of these values. So if I want to look at address line 8, I can see what what the die waveforms look like, or essentially what the waveforms look like. So this is relatively pretty good. The thresholds being H and being low are pretty well exceeded. There's nothing really oscillating around, or it's clearing the threshold range is pretty good. So probably won't see a whole lot of problem with this particular design. So that's reflection. You can see it in, again, tables and visions. Finally, let's take a look at the last one, which is return path. And return path is kind of interesting because it's going to show you the amount of energy that the area or the return path of the energy that you're putting down each particular trace in terms of signal integrity analysis. So there always has to be a return path for the energy that you're sending down a particular set of traces. That energy has to return back to the power supply, or it's lost essentially as radiation, kind of like an EMI effect. So in return path, this gives you a good idea of how effective your ground planes and your return paths are, how well those traces see that return path. To deal with the energy that it has. So by selecting return path flow, again, you want to, the next is the setup area. You want to set up, what plane you're interested in. This only has one ground plane. Here you can set up directed groups, and this is very similar to the directed groups or bi-lane specific kind of relative net selection that we saw earlier in impedance and coupling flow. And then once you set that up, then you essentially start your analysis. That's really the only setup. It's just identify the nets. It'll start the analysis. I'll go ahead and load the results here for return path. And then here it's going to basically give you a return path table. Again, you can look and see what quality factor it has. How that affects this. Like I said, this board is pretty good. It's got some pretty decent ground planes defined for it. So it's setting that up pretty well, and the return you get a pretty good quality factor for return paths on most all of my signals. I did run an initial simulation for one of the data bits just to show you what you can do with this. Any one of these bits that you're interested in, it will simulate that return path and show you the amount of energy and how it's dispersed on the plane. I've already simulated this one, D20, and then so here I can come over. Let me move this out of the way so we can see the visibility. And so that is the one that I set here. That's the one I want to see. And what you're doing is this particular trace, DQ20, is on signal layer 9. So you want to look at the ground planes above and below that particular signal layer. So you can kind of see D20 is right there, DQ20. So you can see how how the return energy is being handled on the ground plane above it, and as well as the ground plane below it. So you can switch between the ground planes and see how well that energy is being absorbed or returned back to the power supply. And like I said, this one's done pretty well. So the ground plane's pretty consistent, and there's no voids or anything to deal with for that return energy. So you can get a good idea of, right there on the fly as you run your routes and run your traces, You can run any one of these particular tests if you have your planes and whatnot in place, and see how effective that route is at propagating your signals and dealing with any kind of return energy. So that's about it. I'll go ahead and turn this back over to Brianna. I think there's some questions.
Thank you, Jerry. And at this time, I would like to open the floor up for the Q&A. So please enter any questions you have into the question pane now, please. And our first question, Jerry, is for the impedance analysis, is the tool assuming the reference plane is the adjacent layer, or can you define it as something else?
By default, it assumes whatever is the closest plane that's classified as a reference. So any kind of ground has essentially a classification or a 0-volt value in terms of the PCB editor's classification. But it's naturally assumed that those 0-volt traces or 0-volt planes are going to be the reference. So it does, and the power planes as well. But that's essentially the thing. It's going to look at what has the closest proximity and report against that.
Thank you. Our next question is, can we also do pre-layout signal integrity simulations?
Yes, one thing I probably neglected to cover is Aurora will also have in its capability with just the OrCAD Designer Professional and Allegro, you still have SigXP. So if you're familiar with that, SigXP was the old topology editor that the Cadence tools had forever. I mean, they've had those tools forever. You could, with that topology editor, you can set up whatever topology, or you can extract nets into that topology and run analysis either pre-layout or post-layout. With the Aurora option, they've updated SigXP now into a new tool basically called Topology Explorer, and it looks very much like SigXP, but it has a whole lot more power. So you can do full-on DDR and serial interfacing. For instance, if I just load up, just bringing it up here, if I just load up a simple topology that I've extracted previously, this is just a driver and a couple of receivers, but this is what it essentially looks like, very similar to SigXP. So you can see, the ability to put things down, put parts down, drivers, receivers, maybe an IBIS model or a SPICE model or something like that. You can put them together, put them together, and then run pulses down, and then take your look at essentially your results. So it's going to call basically kind of a revamped signal viewer, and that will essentially look like this to give you a sense of what your analysis may look like. So let's see, I think I have something here to show. Yeah, so this is kind of what the results will end up looking like. So you can do this in a pre-layout or post-layout, and with the new Topology Explorer that comes with Aurora, or you can use the SigXP that's embedded in OrCAD PCB Designer Pro or Allegro.
Thank you. Let's see. What other questions we have? Where are the parameters set up to check impedances? The parameters themselves are essentially properties of the traces you're laying down. So the impedances it's looking at is purely the copper trace impedance. So it looks at the proximity of other traces, the initial copper makeup, the width, all of those. Most all of that stuff is set up in the constraint manager, where you can actually, when you lay down your trace runs and everything, each particular layer can have a variety of constraints set up so that you know that you're within a certain width and things like that. So all of that set up in the PCB editor tool, just as you would normally. There's no other unique or special work you need to do to define parameters for the impedance flow. It's just going by the constraint manager settings for trace width, the amount of copper on the layers, and the layer depth, the layer widths, things like that. Thank you. So our next question is, how fast is this analysis tool?
Most all of the analysis run about as fast as you saw the impedance flow run. That's the only one I actually ran live, and that ran, what was it, like 34 lines, I think, or 36 lines that I did, 36 signals. The whole board really takes not very long. It takes maybe 15, 20 seconds to do the whole thing, or at least to do this particular board. Some of the other runs take a little bit longer to do just because of the nature of what you're looking at. Most all of them run pretty fast, though. The field solver here is really pretty quick. It's not it's not a super intensive math process that it's trying to do. It's just trying to look at basic, basic field solving, in what they call a hybrid flow, or mainly the X and Y dimensions, but a little bit in the vertical dimensions as well. So it runs pretty fast, to be honest with you.
Great, thank you. So what is coupling coefficient 2%? What if we increase or decrease this value?
What that's going to do is it marks the threshold of coupling that it reports. So setting it at 2% means that any traces that have coupling coefficients higher than, or at 2% or higher, that's what's going to be reported. Anything below that is just going to ignore it. So by adjusting that figure, you can essentially screen or filter what you want to analyze, what it's going to report back, and what you then can analyze and take a look at. So if things, if things below a 5% coupling or something like that are completely uninteresting to you, you can just set it higher and then have those particular trace analysis ignored for anything that falls below that. So that's essentially what it does. It's more of a filtering mechanism for the analysis.
Thank you. And we have, looks like, one more question here. Would you recommend using power planes as reference planes? In what cases, yes, and when you would avoid it?
Not sure when you would avoid it. Obviously, you always want to, the most ideal situation is to have a ground plane as a reference plane, essentially. But what you're looking for here is essentially energy that you're, and it's usually AC energy that you're looking at. So you're basically just looking at a nice clean path back to the power supply, and it can take that path either through the power plane or through the ground plane. But ideally, you would want something on the ground plane to maintain the fastest, least impeded path back to the power supply itself.
All right, thank you. Looks like we're unfortunately running out of time for today. And if you have any questions that were not addressed during the webinar, we will be following up with you on an individual basis. So with that being said, thank you for taking your time to join us today. Thank you, Jerry.
Yeah, thank you guys.